Bob Staley. We've done that too many forums for him in the past few months. So I'm going to cover a few other systems and loads in the house, and then how to model them so you can predict the right usage and the right generation size. But a lot of what I'm going to cover in this next 45 minutes or so are summaries of what the Seeds forums have done earlier in the year. So Gordon and Larry did a whole session on heating systems back in March or May. And then they also did a whole session on hot water. I think that was the March one in hot water. So I'm going to refer you to those details if you want to go through a lot of details. But I do want to hit the tops of the waves on these things. So the heating system is generally in the US about 45% of the energy load of a house. And there are lots of choices for technology used in the heating system. Going back to the traditional fireplace and wood stove, to solar thermal, like we have a solar thermal system in our house and a wood stove. A traditional boiler or furnace. Electric resistance is probably the easiest thing to add because it's cheap and it goes on the exterior of your walls, so you don't have to dig out the walls. And there's new technologies there called radiant panels that actually best mount on the ceiling, and you radiate above your bed, for example. And so the heat feels really warm when you're laying in the bed directly below the panel, and your body is stretched out horizontally to it. So you can do all kind of things with electric baseboard or electric resistance heating, not just the standard baseboards. And if you're doing things like solar heating, adding the electric and only turning it on during the deepest, coldest winter, like a few weeks we had this year, and only using it for that backup heat, then you're not causing it to draw load most of the time. It only draws load when you need it. And then heat pumps. Heat pumps are traditionally more expensive because you're typically doing geothermal or ground source heat pumps where you've got to dig wells or trenches outside. But the new technology that Larry covered a lot back in May is the air source heat pumps, or also called mini splits. And Rob mentioned these. These are really efficient systems brought in from Asia and now manufactured here in many cases. And they are really, they get Energy Star ratings, and they're really easy to install both in retrofit situations and even in new builds that don't require a lot of heating load. But the key is to make sure you buy one that it supports the extra low external temperatures. The first ones that were available here only went down to like 5 degrees Fahrenheit. And of course this winter we had several weeks where we didn't get above 5 degrees the whole day. So you want to make sure you get the minus 15 Fahrenheit type mini split. But they do make them now. When you go to size a heating system, we'll talk about BTUs, and again, BTU is the British thermal unit, but it actually has a realistic measurement. It's actually the energy required to heat 1 gallon of water 1 degree Fahrenheit. So that's by rumor and probably often repeated by people like me in these sessions. That's about the equivalent of 1 sulfur match head of heat, of energy. You can convert between kilowatt hours and BTUs. It's 3,412 of them. So that's one way that's useful, and especially when you get to the modeling discussion, that's a conversion factor that's important. But when you size heating systems, we size them in BTUs per hour. You'll also hear a shortcut of tons, and that's 1,200 BTUs per hour. I'm sorry, 12,000 BTUs per hour is a ton. The problem is the typical way a home building constructor or engineer or heating specialist will size a system is they'll take the worst hour of the winter for your area, and they'll tell you that's the BTUs you need, and you're going to size your heating another 20% higher than that. Because they don't want you ever to complain about your house being too cold. So they'll oversize the system. And that leads to inefficiencies when it's running. It runs too hot, then it turns off because it's too hot for a while. And then all that air leakage and poor insulation drains the heat away and it turns on again. And it gets, so you feel like you're going from hot to cold to hot to cold to hot to cold because it's overheating or overdriving the system. So the standard HVAC contractor will just default to oversizing. In fact, when we went to look for heating systems for our house, we could not find a heating system small enough. Okay? The smallest heating system we could find was a 2-ton heating system, and we needed about 1.5 tons at most, maybe 1.2 tons. And normal homes are more like 8 to 10 tons or 100,000 BTUs an hour. But a well-designed, high-performance home, especially one designed for net zero energy, can be less than 10,000 BTUs an hour. Okay, less than 1 ton. Fuels make a big difference in the heating system, and you can't read this chart, but when you download the slides, this comes from the Department of Energy. It compares all the fuels on many different bases, both the cost, but also the energy density of the fuel. So propane is not as dense of a fuel in terms of its energy content as natural gas is. Wood is also not as dense in fuel, in energy, but fuel oil is. So you've got these different comparisons of how to fuel a heating system if you're using non-electric fuel. But the key is to remember that you're also combusting it inside the home. And so you have that issue of you got a flue, and that's heat going right out the window or right out the envelope. So if you can have a non-vented system, like electric system or heat pump system that doesn't have a flue, then that's easier and better. You don't have to design a hole in the insulation for that flue. And it's honestly, when it comes to energy modeling, it's easier to model too. Not that should drive your purpose. And one of the challenges, though, is these different technologies have each defined a different measure of efficiency. So in air source heat pumps, you'll see things in the efficiency called HFPF, which I don't remember what that acronym stands for. But that's not anything. It's just a testing standard. You need to be able to again convert that into a performance coefficient or a COP, a COP. And you can do that, but you've got to find get that data from the manufacturer to tell them their conversion factor. And in the modeling we're going to talk about, we'll always use a coefficient of performance, because that's basically saying energy times this coefficient means I get that benefit from that energy spent. So electric resistance heating is actually 100% efficient, so it has a COP of 100% or 1 COP. That's because all of the electric energy you put into the resistor is spent right there and it's available to you. None of it goes up the flue. So that's a COP of 1 or 100%. Turns out heat pumps are greater than 100% efficient because they're extracting heat from the environment and making it available to us. So they're putting a little bit of energy in to get energy from the air or from the ground and then bringing it in the house. So there's some energy cost to pump it or move it around and to use the compressor, but you're actually getting a coefficient of performance greater than 100%. And some of these air source heat pumps have greater than 300%. So that's why they're so attractive for a high-performance home. The other thing you need in a high-performance home that has a good air seal, like Rob talked about, is you need ventilation. Unfortunately, in our homes today, with all the stuff we put in them and the volatile organic compounds that off-gas from that stuff, is we have very poor indoor air quality. And when you seal your house up tight, as you want it to for environmental purposes, it can keep those pollutants in the house for longer, and you're not healthy. So there's a standard that requires air ventilation when you have now in effect for codes houses. And when we put these tight air seals on the house, you need to have mechanical ventilation to make sure you're getting enough fresh air. And you can do that with just fans, but if you're sending the stale air out that's been heated up in the winter, it'd be really nice to save some of that energy and heat before it goes out to leave it inside. So there are these systems called heat recovery ventilation, or you'll also may hear it as energy recovery ventilation, HRV or ERV, that are available that will take stale air from the bathrooms or other places where you want to get rid of odors and run it through a heat exchanger from fresh air coming from the outside and heat that preheat that fresh air before distributing it into your house. So that's what that's the basic concept of a heat recovery ventilation system. Outside of Northeast and other places where you have high humidity and air conditioning, we probably hear more about an ERV, because that actually recovers the cooling as well on the reverse side in the summer. But around here, we don't see ERVs very much, and they aren't worth it because we don't do as much cooling as many other places in the country. The second largest energy load in the house is hot water. And TEAM, when TEAM does the energy assessments, hot water conservation is an important part of that. And most people don't think about saving hot water. But most typical US residents use 25 gallons of hot water a day. That's a lot of hot water, a lot of energy going to those BTUs to raise the water from 50 or 50 degrees Fahrenheit when it comes into your house to the 120 degrees you want it when it comes out of the faucet. But if you do reasonable conservation techniques, you can get that down to 10 gallons or less. Typical, even families with little kids can use 15 gallons a day instead of 25. There are a lot of system choices, and again, Larry and Gordon went through a lot of that. But one of the neat ones that's new is the air source heat pump built into the water tank, hot water tank. It's also called a hybrid hot water tank. It works well if you have a house with an unconditioned basement, so you're not heating the air to then have the hot water tank take the heat out of the air to heat the water. You don't want that. So don't use a hybrid hot water tank if you're putting it in the conditioned area of your home. Only use it in unconditioned area. So it's not for everyone, but it's super efficient. It's like 230% COP.
You mean like in a basement, but it's unheated basement?
Right. An unheated basement or maybe an unheated garage.
And they also dehumidify too.
Yeah, and they also take moisture out of the air and condense it. So if your basement is already wet, it's a great dehumidifier in addition. But it's not for everyone. Plug loads and lighting matters. This is back to the behavior of the resident, of the occupants. So the instructor that both Rob and I took a class in zero net energy building design. The company he worked for built 6 homes as net zero energy homes, and actually monitored the occupants of the 6 homes for 2 years. And so he's comparing the results of those 6 homes with standard home. And the occupant usage is very different, especially for electricity for plug loads. So it really matters the behavior of the occupants. So recommendation, as you'll see, that if you take the team assessment and their report, Maximize your use of passive daylighting and LED lighting. Cooking appliances, get Energy Star appliances. The latest technology there is an induction cooktop. You've got to use steel or stainless pots and pans. You can't use copper or aluminum. But 100% of the energy goes from the cooktop into the pan. It doesn't go outside of the pan. It doesn't go up the flue. It stays in the pan and cooks the food directly in the pan. So it's really super efficient. And it's fast like gas cooking is. And I love gas cooking because it's fast on, fast off, unlike electric resistance. But induction has that same behavior. Refrigerators, freezers are running all the time. Get Energy Star, and even look, these days the Energy Star rating doesn't mean as much as it did one time because the manufacturers are producing more of them. So actually look at the meter on the tag when you buy and make sure it's as energy efficient as you can get. The solar clothes dryer, the clothesline, is super efficient. Don't have to put any energy into it. But if you really insist on needing a dryer, and sometimes in winter you do, look at the condensing dryers like they sell for New York City apartments that don't need a vent, and therefore don't need a hole in your envelope to vent that. So they're another way of saving electricity, and they extract the heat from the clothes without burning things. Plug loads, beware the phantoms and the zombies. There's so many electronic gadgets, TVs, stereos, computers, phone chargers, that when we leave them plugged in, even though the phone is not attached to them, the transformer in there is burning electricity without charging anything, and just draining away and costing you money from the electric utility every hour. So that user behavior matters. It's really important. Okay, so let me switch topics a little bit into modeling and being able to predict how much energy you need when you're doing a house design or a retrofit design, or just want to know how much your house should be using. There are all kinds of detailed models available. The Passive House Institute I mentioned earlier has a hugely detailed model that you have to go get training and pay an annual fee to use their model. You don't need that level of detail for almost every purpose, unless you really want the certification. Mark Rosenbaum, who taught the course that Rob and I took, produced a set of spreadsheets that I'm going to show you here. They're his spreadsheets, so I can't share them with you, unfortunately, but I can show them to you. And it's a basic model. It's only about 8 sheets long, and it enables you to model everything in the house to get a total energy budget. And the basic model is, it's looking at the total heating load and ventilation load minus the passive solar gains and other gains you get from internal waste heat. That waste heat can be the electricity that you're burning in the house, like lighting. That light is converted to heat, and that heat is useful to you inside the house. But your body is also the equivalent of a 100-watt light bulb when you're just sitting and walking around. Now, if you've got an exercise room in your house, that's much more than 100 watts while you're exercising. But generally, 100 watts is a useful measure of stuff in a model like this. But you do have to multiply that heating load by your coefficient of performance. So to get actually the electric load of the heating system. Now, if you've got a fuel-based heating system, then you have to modify it by the fuel density as well as the COP. Okay? Then You've got things like the domestic hot water load. What does it cost? Where is the energy going into to heat your hot water? The energy used in your lighting appliances and plugs. And then and only then do you subtract out the generated power from your PV system or other generation. So first off, heating design. So how many people know the units that come in the R value of insulation? We talked about R value a lot today. I didn't know this until I took the course. There's actually a set of units that go with R value. It's not just a unitless measure of comparison. It's actually got a purpose, and I don't remember what the units are now that I asked that question. But the idea is you can actually measure the heat loss in BTUs per hour through an insulation as the conductive heat loss by taking the area of the wall, in this case, minus times the difference in temperature between the outside of the wall and the inside of the wall, divided by the R value, and you'll get the BTUs per hour. So, a 100 square foot wall, 10 by 10 wall, 70 degrees inside, thermostat setting, at minus degrees outside in winter. That's at an R20 wall, that's 350 BTUs per hour through that 10-foot wall, that 10-foot square wall. Now, you got to sum that out over all the other walls and windows, foundations and roofs of your structure. But then you can imagine doing that in a spreadsheet, and you'll get the BTUs per hour your house needs to stay at 70 degrees Fahrenheit. That's the basic idea of the model. But then you also have to account for air infiltration and ventilation losses. Okay, so that's just the conductive stuff. When you're doing convective energy loss, you're losing heat because the air is moving across the boundary. So you've got to measure a house's infiltration by doing a blower door test. And we haven't talked about blower door tests here, but I think it was covered in a previous forum last year, not this year. So blower door tests are really useful. They can measure the actual loss of air through the stack effect that Rob was talking about. And that's an important measurement for the model. You can design the different wall segments and assemblies that Rob was talking about, have certain design qualities to say, well, that's a design to get to this level of infiltration and that level of infiltration. You should target an infiltration of about 0.5 CFM, cubic feet per minute, at 50 pascals per square foot of shell. That's really tight house. But that's the design target that Rob mentioned earlier too. But you also have ventilation, which is that intentional bringing in of fresh air. So in that case, you use the efficiency of your HRV. So those two things have to be included in addition to the BTUs through the walls and the windows. This is a picture of the spreadsheet that does that. And I'm not going to go through it. But this is the sum of all those details then. For every wall, windows, slope ceilings, skylights, flat ceilings that they're insulated, opaque doors versus glass doors, they have a different type of insulation. And then the slab on the foundation wall or the foundation wall height, the infiltration, the ventilation, all those add up and you get a coefficient of building load. That's basically how many BTUs per square foot of shell am I losing per degree of temperature difference. Don't worry about it. But you can see in this house at the bottom, it's 10,450 BTUs per hour is the worst case in the winter. Okay, less than 1 ton. And this is basically following the rules he mentioned, rule of thumb, R20 foundation, R40 wall, R60 attic ceiling. Okay, so it's doable.
And so again, that's about 1/10 of what a normal house would use?
Yeah, that's 1/10 of the load heating load of maybe a normal large house. And then the next step is to annualize that. So that's the load per hour in the worst hour of winter. Now, how do I take the worst hour and get a whole year view? Well, you annualize it. There's a great tool, and it used to be on my utility bill, but I don't see it anymore. I think PPL stopped producing it, called heating degree days. It's basically the amount of, it's averaging the min and max of the temperature of each day compared to typically 65 degrees Fahrenheit. So if you're heating it, let's see, today's heating degree load would be negative, right? Because it was above 70 on the average today. But if it was high of 30 degrees Fahrenheit and a low of 0 degrees Fahrenheit, the average would be 15 degrees Fahrenheit, and that would be 55 degrees different from 60, or 7, sorry. So that would be a 55 heating degree day. But you can calculate it, or you can go to this nice website, degreedays.net, that'll give it to you for your area. So it picks a weather station and looks at the history of that weather station. And I did it from Mount Poconos Airport. And so here, or that location in 2011, that was a warm winter. Remember that winter? It was only 7,350 degree days for the whole year, heating degree days. But this past winter was 9,100, excuse me. So the average over the past 3 years was 8,350. But it changes depending on how far back in time you go to look. So all you do is take that coefficient we calculated on the previous sheet, multiply it by 24 instead of get per hour and make it per day, and then times the heating degree days gives you for the whole year. And then you subtract the heating gains, the passive heating gains through the glass or the glazing that Rob talked about on the south side, the east side, and the west side. To get that calculation, you need to know your window solar gain coefficient. I lost a letter in there. Heating coefficient. Plus, you need the energy that the sun puts on the window surface. Well, you can get that energy level from the National Renewable Energy Labs. Has a nice model called PV watts that we use in solar installation modeling. But it will also tell you the amount of BTUs that goes on the surface of that window over the whole year. So you can calculate then from that the amount of passive gains you get from your glass, your south-facing, east-facing, and west-facing glass. But you don't want to do that for the June and July, because you usually open your windows or you have cooling going on. So you don't use those gains 100% during every month of the year. You adjust it for a seasonal adjustment factor. And then lastly, you convert those BTUs, those annual BTUs, which are way up in the thousands or millions at this point, you convert it into kilowatt hours. So that spreadsheet does that. Trust me. I spent a lot of time digging into this because I'm the engineer. I got to explore it. Got to make sure it's right. Mark also provided us a nice hot water load comparison for all the different type of hot water technologies, whether you use solar hot water or a hybrid hot water system or some other system that has a COP. So you can calculate the BTUs per year to heat the hot water, and like here it's 4 million. But that's incoming temperature of 50 degrees, outgoing temperature of 130 degrees, 15 gallons a day for 2 people. Or convert it to kilowatt hours, and it's 1,200 kilowatt hours. Okay? Now we got to put it all together with the other electricity we use in the house. So we do the heating COP. We just estimate that we spend 273 kilowatt hours a month on plug loads and appliances, non-heating types of appliances. and we get a total of 6,000 kilowatt hours, 6,508 kilowatt hours per year. Now, I was doing a home assessment today or yesterday with a family, and they got that amount in 1 month. Okay? So, on the electric. So, this is a high-performance house. And it's that level of difference between 1/12 of maybe another home in your neighborhood is possible if you build a high-performance net zero energy house. And of course, you got to add cooling. If you do air conditioning, you got to add cooling costs. The last step is sizing your renewable energy system to make up for that 6,500 kilowatt hours. Well, 6,000 kilowatt hours, 6,500 kilowatt hours is not that big. If I use this spreadsheet, again, expands out, but if you use the latest SunPower systems, which are 320 watt panels, which is a little higher end than what Blair was talking about here last month, that'll fit on a 30 by 10 foot roof. 18 of them to get you a 5.7 kilowatt PV system. And you'll make back 6,600 kilowatt hours that year, on the average year. And it will only cost you about, actually this number is 3.75 cents per watt. That's probably too high right now. It's maybe $3.50 a watt instead of $3.75 a watt. So $20,000 for the PV system. But if I didn't need a heating system, because I only used a mini split that was maybe $800 or $1,200 instead of a furnace that cost $6,000, $8,000. Yeah, I've got at least $7,000 to put forward this PV system instead. And then for the PV, I get 30% federal tax credit for the PV system, plus the SRECs that we talked about last month. So yeah, this is quite affordable if you think of it as an investment that pays you back in the future years, but you have to pay more for it initially. We thought Rob found these great examples of other homes that are also net zero energy. And Rob, do you want to talk about these?
Well, these were submitted in that award program for NESI. And, some people have this notion, like what an electric car looks like. And electric cars used to be pretty geeky, and now they're pretty sexy. Well, net zero houses don't have to be like that first example we showed, just the pillbox house with straight walls. They can be pretty sexy looking from an architectural standpoint. But the cost per square foot is going to be a lot higher because you've got all these angles and roof forms, and you're going to pay for that because you basically had a larger envelope on the outside. So a house like this, the other one was like $100 or $105 a square foot. These are going to be $200 a square foot because you're getting all that architecture, which may not be necessary from an aesthetic standpoint, but you can if you want to. And I think a lot of people in the 1% of the country are deciding that green is really sexy, so they want to have, they're going to be driving a Tesla car that they pay $10,000 for, but they can get free electricity in California and plug it in. Or they want a house like this. The house on the right, these people have an electric car, and they wanted to have, be able to plug it in and charge it. So they have, I can't see it all, but they had, I think it's 6 kW array just to charge their car and heat their house, but they put another like 15 kW on the roof just to put back in the grid because they thought it was the right thing to do, and they also wanted to get all the SRECs checks from that system. Yeah. So you can see that the whole area of their roof is just covered with PV. So they've got, I can't remember what the number was. It's like 15 or 20 kW of roof array, but they're doing the right thing. So I guess I was interested to see what the range was, and I was on the review board that had looked through all the submissions to make sure you checked all their energy bills to see whether they actually were net zero or not. And these two houses both didn't comply with those requirements.
This one is yours.
All right, a builder came to us and wanted to, he did ground source heat pump systems, he did radiant heating systems, he did PV installations, and he wanted to build a spec house. He has a number of property that he wants to sell off lots, and he wants to build nothing but net zero energy houses. So this was his house that he designed, and he had 11.25 kW on the roof, but he had a ground source heat pump, which is like really energy intensive, and he has a radiant floor heating system. But he installed it, and he's happy. He thinks he's reaching net zero, but he was the house that only had the 1.5 inches of polystyrene insulation underneath the radiant floor slab. So I think he could have done better than that. But I think that he was getting, okay, his house, he thinks is going to be selling out. It's a 2,500 square foot home. This has a lot more. He's got bonus space above the garage. It's going to be a grand flat. But I think he was saying he can build this for roughly $150 a square foot, including the PV array on the roof. And in this past February, which was really cold, he only had a $5 electric bill. And the reason he had the electric bill was he forgot to turn off the backup boiler for his heat pumps. So he's got an incredible envelope because he had the SIPS panels, excuse me, the ICFs, insulated concrete form on the outside walls, and he's probably got about 24 inches of cellulose in the ceiling of the roof. So he's got a really great envelope. His website, it's www.zeroenergyhome.es, HOM.es. But he's trying to get people to realize that they can build net zero energy homes at a market rate, the same price that other people are paying for conventional houses. You're paying more for your PV and that stuff.
And he's operating here in Pennsylvania, and including Northeast Pennsylvania, New York, and a few other states.
And Massachusetts. He does an awful lot of work in Massachusetts because Massachusetts is so progressive, and that was that first house that we showed as far as what
So it can be done, and I think that's our summary point. Is it's possible. It's not that expensive. Yes, it's more expensive than standard construction, but it's worth it because it pays back to you over time. It's harder, but it's also possible in retrofits. Things like that Larson truss external of the foundation, putting a pseudo floor on top of the foundation floor to insulate it. It's possible, but it's disruptive in a retrofit because you've got to tear a lot of things out and redo a lot of things. So that's a whole category in itself, is major energy retrofits. Overall, I'd say that details matter. And Rob burst through in 45 minutes a lot of details. So if you want to get serious about net zero energy, think about the details. Hire people who will help you think about those details. Energy modeling helps because that then provides something to feed back into integrated design process that Rob talked about. If you make this change to the house envelope, what does that mean to the heating system? Do I need to upgrade the heating system to a 2-ton system instead of a 1-ton system? If I change the window amount of glazing on the south side, is that going to affect things? You know, if I orient it differently, how does that going to change things? So that model, the energy model, gives you a foundation to answer those questions with numbers instead of just guesstimates. And we really think high-performance homes and buildings of all types, not just homes, are the way of the future if we're going to address climate change. It's my personal feeling. And then we wanted to give you a bunch of resources, so this will be on the website when you get the materials. Endless Mountains is the builder that Rob was talking about there at the last example. And the Passive House Institute, some people were asking me about it. And we want to acknowledge the instructors for the courses we took. Rob, you took a special course on insulation, right?
And so out of those details came from Steve Basic, I think his name is, and he's standing on the Larson Trust to show you how strong they are on the right-hand side there. And Peter Yost was one of the founders of the Building Green company, and so they had this book, and he was asking about rock salt insulation, and they talk about it in this book. So I'd really recommend getting that publication because they do the whole system.
And then we both took this course from Mark Rosenbaum. It's an online course, 10 weeks, but to finish the course, you have to design a net zero energy house from scratch to finish as part of it. And not being an architect and not being a civil engineer, it was a real stretch for me, but I really benefited greatly from it. I just wish I had done that before we built our house, because I would do so many things different. But it's once in a lifetime chance to build your perfect house. That's done. You don't have to worry. Mark is a really great resource. He's one of the standards at NESI, and he's always doing good workshops at the Building Energy Conference, which is held in March in Boston every year. This year, I think, is the 15th year coming up, so it's a really good conference. So thank you, and we'll take any questions. Yeah, Chuck.
The Larson trusses, are they something that you then purchase, or can you manufacture them yourself?
Both ways. Some people do them on site. You know, you can just have a 2x2 on the outside, a 2x2 on the inside, and brace it however you want to by nailing stuff on there. The ones that I showed on the slide were prefabricated, you know, from a truss manufacturer. But it's just a question of just making them strong enough to support the load that they're going to have. But you can build them, just like you can build roof trusses on site too, but you have to do the engineering.
Right. So there's no infringement of copyright.
Oh no.
And,
You can put your name on them and probably.
Anything else?
ground source heat pumps. What's the latest on kind of the efficiency of either shallow tubing in the ground or deep wells or?
Those are all site considerations as far as what your soil conditions are. But Mark Rosenbaum, our guru, feels that the mini split systems are just so much simpler to install. I mean, they have them now that the owners can install them themselves. They're just sort of plug and play sort of models. With ground source, you either have to drill wells or have shallow loops. There's just an awful lot of hardware involved in them that are usually sourced to a number of different contractors. You've got a well driller, then you've got somebody that's going to be installing the compressors on the outside of the building. You've got somebody else that's going to be running the heating ductwork or whatever on the inside of the building. So there's a lot of different things, and if something goes wrong, I mean, there was this one project where the Trinity Church in Boston didn't have a lot of land, but they put in a ground source heat pump by drilling like 12 wells, on the property. And then they were monitoring the system because they had to do the commissioning afterward. And they realized that the system wasn't really operating as it should because one of the pumps was running continuously. And it was just burning up a lot of energy, pumping the fluid through the system that didn't need to be there. And with a mini split, you would have known that right away because your temperature inside the building would have been going. But this was just running. So the complexity of ground source is, to me, with a super insulated or high performance building, is being eclipsed by the simplicity and the COP of the mini splits, which, as Jack said, are like 2.5. So every unit of energy that you put in, you're getting like 2.5 or 3 units of energy out of them. And I don't think you can get the same COPs out of ground source heat pumps. And the initial expense of ground source systems could be like $20,000, $30,000, where the mini splits are just a fraction of that.
I think you're right in your conclusion about mini splits versus ground source, but my recollection is that the ground source heat pump has a COP of around 4.5. Correct me if I'm wrong.
I don't remember, but
The typical, ground source heat pumps have higher COPs, but much higher installation costs.
Right.
And the trade-off, I mean, if I had it to do all over again today, I would do mini splits rather than ground source, just because of all of those factors.
You know, we installed a solar thermal system on our house and spent like $9,000. And then when Mark said, when I took his course, and said that if you had a heat pump hot water heater that actually acts as a dehumidifier and put it in an unconditioned basement, it would have been perfect for our house, because we've got an old house. We got a dehumidifier that's running, you know, through the summer months. And if we had a heat pump hot water heater, we could have solved both. We could have been getting heat out of that operation. You know? So,
Yeah, it actually does show the ground source as being more efficient
Yeah.
than air, and I believe that, but the cost is the big
Yeah,
difference.
right.
right.
Yeah.
I heard that on the ground source heat pumps too, that if you're not very careful how you install them, that the water can collect in there and you can have a mold problem if you're not really carefully installed.
Collect where?
In the pipe. On the ground source, if you have the horizontal,
Oh, if you have a horizontal.
And not
Interesting.
vertical.
I don't know. I don't
know
think so.
what the
I don't
problem
think
is.
so.
Yeah.
Because it's charged basically full of water with essentially purged of air, and
Okay, maybe that's it.
I don't think that's going to happen.
But getting back to your initial question about the you know, how do you size it? There are so many unknowns in each site, but you know, if you're drilling wells, you know, how deep you have to drill and what the soil temperatures are and all that. There's a lot of things that are a little bit hit and miss on the ground source.
On our property, we looked at it, and we couldn't do the horizontal trenches because we had so many rocks in Hawley. We're basically in glacial moraine, so the rocks are everywhere. So they wouldn't do trenching. They had to do vertical wells. By the time we, you know, figured out we couldn't get a 1-ton heat pump because they didn't make them that small, we were shot. You know, that cut that out right then.
Yeah, and I think they did price it for us, and if I remember, it was 20
It
to
was
30K
it was
somewhere.
80% oversized.
It was huge.
Yeah, it was
Yeah.
outrageous.
Couldn't get it small.
Yes.
Probably everybody knows this, but I don't. The mini splits that you have, you said go to an outside temperature of -15, is that what you would
You
recommend?
can get them that low, yeah.
Yeah, the Mitsubishis are 65% efficient down to 15 degrees below zero.
And what happens if you have the 10-degree one, they just don't work? Is that what happens, or?
So they get less efficient as you get lower temperature, and they usually have an electric resistance element that kicks in to make up the difference.
Gotcha.
But you need to make sure it actually has that. If it doesn't, it'll just stop working.
Yeah, Edward said that the mini split that they have in the office there stopped working.
Yeah, the
This-
condensers
this-
freeze up when you get temperature, outside temperature gets too low. They get ice forming on the outside and then it shuts down until outside temperature melts the ice.
And what was it when the Mitsubishi, what? You said-
It's 65% efficient down to -15.
Yeah. So
And
you can get-
at zero, it's 100% efficient still. So it's really, really, you know, if you're going to install one, that's the unit to look for. Fujitsu probably has a similar one.
Yeah, it's amazing these days. One of the exercises we had to do for the course was go find a mini split spec to match the spec of a load. And so, you know, we went off and researched, you know, 6 different manufacturers to find the right spec that fit the house we were designing. It was fun.
You said you couldn't find a system small enough. Is that how you solved it with the mini split, or?
No, this was, we built it was 6 years ago. So we ended up with a solar thermal system with just an electric resistance backup. So our heating system, when we finished construction, was just an electric hot water tank. No heating system, no traditional heating system.
Gotcha.
Radiant
Electric hot
floor
water tank
heat,
that
radiant floor.
pushed hot water through our radiant floor.
90-degree water.
90-degree water.
That's all.
And then we added later a solar thermal hot water system so that we now only use that electric in backup cases where if we have a week of cloudy days, then we have to turn that on.
So technology is changing at an incredibly fast rate. I think we all realize that. I mean, when we first started practice, anybody that had an air-to-air heat pump system realized that after it got down to like 30 degrees or 25 degrees, they'd have to convert to resistance heat to get it to work. And now, when I took the course, it was like below 5 degrees, Mitsubishi wasn't performing. Now you're saying it's down to 15 degrees. So with it's converting from an AC to a DC motor on a compressor, they're able to get incredible efficiencies because they only run the compressor at the speed that's necessary to deliver the temperature that you need. It's just an amazing technology.
Are they installing the air source heat pumps for central forced air systems, the high efficiency?
You can get them.
We did
for
that
multi-
we did an animal hospital in Plains, Pennsylvania, near where we live, and it was 12,000 square foot building, and they used the Mitsubishi the city multi-system, which basically, it's pretty crazy, but they can break a building up into zones, and it's an air-to-air system, but they can take heat, like in the perimeter of the building, they fluctuate between heating and cooling during the year, but the center core of the building, they basically air conditioning all through the year because of the lights and the occupants and the negligible heat loss from the center of the building. Well, they can harvest heat from the perimeter of the building and run it through the center of the building and basically redistribute that with using the same heat pump system. But the controls on that system are just incredibly elaborate. It took a long time to tweak it all to get it to work it out. But the efficiency on, and that was also a building with ICFs, and so we gave them a really good envelope, and they said that their heating bills are just negligible compared to what they were. So you can use the same technology on a larger building. It's just bigger compressors and bigger capacity.
But it also means you don't need as many vent pipes running, you don't need your ducting as much. You still need some to go from a central unit out to a few parts, but they're shorter runs and it's not as lossy through that venting, through the ducts. Any other questions? Yeah.
When you see all of these developments where a builder comes in and builds 30, 40 new homes and he's selling them, how much can I be assured that somebody in that housing development or that contractor is caring about any of this stuff?
Not very. Now I do know, some builders like the Endless Mountains guys, they're committed to it, and there are lots in California that are highly committed to it. There are incentives in some states for builders to build high-performance homes.
But developers in some areas of the country, like Seattle and the West Coast, realize that if they build a whole subdivision with net zero energy homes, and I don't know whether I have the website for that, zerohomes.org or whatever you said, but they realize that they can turn over the houses so much faster if they're high performance that their profit margin goes up because they don't have houses sitting, they sell the houses before they finish building them, where everybody else builds the spec houses and then waits, a year or something before somebody actually buys.
Well, I guess my question is, how would I know
that the builder's performing? Well,
Yeah.
you've got to do your homework, and I think you've got to find somebody like Endless Mountains. I'm not endorsing him, but I think you have to somebody that's motivated, that wants to do a high-performance home, and is marketing themselves as a high performance, and demonstrates to you that their buildings are actually performing to spec.
And there are certification agencies, particularly home energy, what's the RS? HERS, you'll see HERS, home energy something specifications.
Right.
So that if you can, it's a rating system, that's the R,
Right.
rating. Home energy rating system.
So a conventional home that has a HERS rating of 100, and a zero energy home has a HERS rating of 0.
All right, well, now that leads me to my other question. If I have a traditional old house now and want to think about converting it, how do I find the right people to do it?
Word of mouth, I think you've got to find somebody but again, the contractor that built your house had never done a super insulated house before. But he just sort of, this little bird is talking to him saying, this is the wave of the future. Energy costs, if they're going up 3% every year, they're not going to be able to build big houses and maintain them and heat them at the same level they were in the past. So he started thinking about that. And he was really anxious to work with us to work out all these details, to do the air sealing and all that stuff. So you have to find a builder that's motivated, first of all. And then you have to find a builder that has a track record of actually completing it. But, you know, on a lot of the projects that they talk about in Nessie, where an owner-builder, gets somebody on staff, eventually, the first time they go through, you talk about spray foam and air sealing and all that stuff, and the builders are just saying, oh, I don't want to do that. Blower door test, no, I don't want to do it. But you get them excited about it, and it becomes a game to see how tight they can make the house, and they get really competitive about it. Then they start